I'm going to talk about topic 6, that is charge interactions. The first point that is observed is the concept of electric charge and its interactions. Here we have to mention the electron, which has the negative charge, the proton, which has positive charge, and the neutron, which does not have charge at all. The valence electron, they are the atoms that defines the energy level of an atom, the last energy level, and they vary according to the type of material. Then here we have three types of the electrons materials. First one is the conductor, that is the material which permits the electron to flow freely. The semiconductor, that is the material which permits the electron to flow freely, but sometimes the insulator is the material that impedes or avoids the free flow of electrons from an atom. One example of that is the plastic, or the sulfur, or even the air. Then we pass to the Columbus law. The Columbus law states that the electrical force between two charges objects is directly proportional to the product of the quantity of charge on the objects and inversely proportional to the square of the distance between the two objects. Here we have the formula expressed. First one, we have the F. The F is the force of the attraction. The R is the distance between the two charges. And here we have Q1 and Q2, which are the two charges that the problem mentions. And the constant of K, which is 9 times 10 to the 9 exponent. It's expressed in newtons times meters squared divided by coulombs squared. And then the superposition of forces. Here is when we add all forces to calculate force inverse and then add them. This is going to depend on the direction of change both, and it can be positive or negative.
Here we have an example of the topic number 6. In this problem, they are asking us for the force. We have the charge 1, the charge 2, and the distance. The formula says that we have to multiply the constant by the charge 1 and the charge 2, and then divide it by the distance in square.
And then we divide the values, and this is the result in newtons.
Topic 7 talks about electric field. The electric field has two forces, that is attraction and repulsion. The attraction force is when two charges attract each other, and repulsion force is when two charges separate each other from one of them.
Well, to determine the direction of an electric field, a test charge is used. Using a possibly charged body as a control charge and bringing a test charge close will indicate the direction of the electric field. In this case, the electric field is the E and the F are the points into the direction. If the force over a charge is of repulsion, then the force F points into the opposite direction of the electric field, like this way. Is the opposite direction.
Now we are going to talk about electric field lines. Here we have a proton which has positive charge. Then we find that field lines are going away from the proton. And in an electron which has a negative charge, the field lines, or in this case the electric field, is going to attract to that electron.
A point charge, in this case Q, produces an electric field, the E, in every point in space. Like in this case, we'll look that the point charge are making the electric field in this. This is the electric field, the E, and these are making a field.
Here we have a formula that is a scalar form of the electric field. Here we have electric field, the force, and the test charge. Here are the...
In this case, the E, like I say already, is the electric field magnitude. The F is the electric force between two charge. The charge are the Q. The Q is the test charge in this case because it has a zero. And this is the other formula that is going to explain my teammate.
Here, as we saw the Columbus law, we have to substitute that data to get the formula of the electric field of a charge, which is the same. The E is the electric field magnitude, which is in newtons divided by coulombs. The constant, which is 9 times 10 to the 9. The charge, which is the Q. The
In this exercise of the topic number 7, we have to get the electric field. For this, they give us the charge and the distance. For the charge is in nanocoulombs. We have to convert it to coulombs. That is 4 times 10 to the minus 9. And the distance is in centimeters. We have to convert it to meters. That is 0.20. Here's the formula. We have to multiply the constant times the charge and divide the distance to the square.
And then we substitute the values, and this is the result on nanocoulomb.
Electric flux are the electric field lines through a surface area called electric flux. Here in the figure shows 4 equal boxes with each with a different charge magnitude. We can observe these ones. So the electric field and the area are vectors. They have a magnitude and direction. The electric flux is represented with the following question. To calculate the electric flux, the magnitude of electric field and area, we can do it as a following equation. Where electric flux is nanocoulombs, E equals electric field, A surface area, and angle between the surface area and the electric field. The Gauss law is used to calculate the electric field and its alternative to Coulomb's law. The previous statement can be expressed by the following formula. This is the formula. This formula is now an integral of Gauss law. The integral means that all electric contributions over very small areas of the sphere are going to be added up. The electric flux is going to be calculated by dividing the value in closed charge by the permeability constant. If one charge is enclosed, you will add a probability that is using the charge sign and divided by the permeability constant. This is shown in the following equation. If we want to calculate the electric field of a point using Gauss law, it will let us to use this formula. However, there are charges that are not point charges. For instance, a charge rod or charge ship. Here are some formulas that we need to consider, like the linear charge density, the surface charge density, and volume charge density.
For the topic 8, we have the electric field, and they give us the permittivity constant and the density. Here is the formula, and we have to divide the density over 2 times the constant.
Then we substitute the values, and the result is in 9 Newton over Coulomb.
Topic 9. Electric potential energy. Electric force is a conservative force. When a force is conservative, then the work depends only on the initial and final positions. We know that potential energy depends on the position of an object. Thus, we can express the work done by a conservative force with the next equation. This can be observed in the following image. This is the equation we can use. The indices A refer to the initial and final position respectively. Comparing the electric potential energy to the equation energy mgh is where mg is the gravitational force and h is the height of an object with respect to the ground. Applying the electrical force Fq times in electric charge instead of the gravitational force mg, we expressing position as R, we have the following here. Where Q is potential energy, Q is test charge, E is electric field magnitude, R from one plate to the charge. The water by the force is then this formula. The subindices A represent the initial final position that this can be observed in the following image. Here we have the figure that gives us the work on potential by a uniform electric field. The concept of electrical potential energy. This means that when the particle with a positive or negative charge moves within an electric field, it exerts an attractive or repulsive force that performs a work of the particle. This can be expressed in terms of electrical potential energy as a real topic. To calculate the potential energy of a point charge due to the electric field of another point charge, we can use the equation 9.2, like we said in previous. This is the charge we can use. Instead of using E as electrical field, we can substitute by the equation of the electric field on a point charge. When the equation becomes to this one, where U is potential energy, with K is a proportionally constant, with Q is the magnitude of one charge, Q of the second charge, R distance from one charge to the other charge. The work of electric force when the charge moves it is this formula. The collection of point charges.
For topic 9, we need these facts. The facts are the charges and the distance between the charge. Then we use this formula for the potential energy using the constant and the distance between this charge and the charges. And then the first charge plus the second charge plus the third charge. And then the result of the formula is measured in joules.
Hello, this is topic 10, and the topic 10 is electric potential. The electric potential of a point charge and the system of the point charge. The electric potential of work per unit charge to analyze in the previous lesson can be calculated for both point chargers and systems of point chargers. The electric potential associated position for single point can be calculated by the following equation, where V is electric potential with equals to both, Q is the proportionally constant, Q is charge C, and R is the distance from the charging of a given point. Here is the formula. Some instruments is trying to have a second charge on a specific point to have potential B. The potential has the ball as a unit, which is 1 ball equals to 1 joule divided by 1 column. 1 ball is instead of the 1 energy, which equals to joules per column of a charge on a specific point. To calculate the electric potential due to a collection of point charges, the following equation is used. It's like using the sum of force times Q times Q1 into R. Why? Potential difference between points, the higher per unit positive charge, the electric forces perform to smooth a non-test charge from a point high potential to a point of lower potential. This is expressed as follows. Here is the formula we have to use. The subindices A and B refers to initial and final positions. The work per unit charge is work done by the electric force to move large particle from a point of initial view A to a point of initial view B. The per work is charged is also independent of time by taking of the charge. If the energy of a ball is going up and down, the energy imprinted in the kick is transformed in kinetic energy, which equals to K. As the ball rises, the kinetic energy will be transformed into potential energy, which equals U. When the ball goes down, the potential energy will transform gradually into kinetic energy. The equation describing the relation between work and energy can be expressed as follows: which equals U times plus K plus W. That equals U2 plus K2. Where U2 is the initial potential energy, U2.
Okay, now for topic 10, we have these facts: the charge 1, charge 2, and the what?
Potential.
Potential energy, sorry. But we have only this formula, so we have to change this formula into this formula, changing the distance and
The potential,
energy. So we substitute the values, and the result is measured in
meters.
meters.